Welcome to Breadboarding. This is video 44 in the Breadboard 8088 PC series. In this video we're going to be looking at what happens when you power a PC on. And this photograph is actually from a compact Desk Pro PC that I've got from the late 1990s, early 2000s. We're not going to be looking at the Desk Pro to look at what happens with PC power. It's a little tricky to get into the innards of it. So what we're going to do is use the Breadboard PC. This is the current state of the Breadboard PC. We've got the Intel 8088 processor down here. We have a little LED display and keypad that we use for doing some of the monitor so that we can do some debugging without having to resort to loading up the full DOS operating system. And we have the EPROM that has the BIOS in there, half a megabyte of RAM. This is a video card over here, produces monochrome display output. Then we've got the floppy disk drive and the controller, hard disk drive controller and the hard disk drive, and then we've got various other interrupt controllers, timers and things like that up there. We've also then got a PS2 keyboard plugged in, and there's also a mouse port there which we're not using yet. So if you want to know more about the Breadboard PC, there'll be a link at the top of the screen and the description below where you can watch a summary video that gives an introduction to the project so far. So let's have a look at what happens when we power a PC on. So this diagram I'm going to be using during the video just to come back to. So the initial part is where the PC power supply switches on. There is a period of time where the output voltages will not be stable, and so the power supplies on PCs have a signal called power ready, and the power ready is that what's then used to signal to the computer that it's actually okay for it to power up. Now in the Breadboard PC we actually use a power supervisor circuit which actually simulates this because I'm using a bench power supply for providing the power here. The key thing that this circuit does is establishes when the power is stable, and then will also produce a reset output to keep the CPU in reset condition until such time as the power is stable and the CPU can then be taken out of reset state. So let's have a look at the logic analyzer that I've got hooked up to this and see what that involves. So what I've got here is just three signals here. We've got the 5-volt power line here, the reset output that actually resets the CPU. So the reset on Intel PCs is active high, unlike a lot of the older 8-bit micros that tend to be reset active low. So when this reset signal is high, then it will mean that the CPU is in the reset state. And you can also see here that we've got the reset button. If you see down the bottom right hand corner, just that red button down there, so there is a reset button on the keypad. Now early PCs didn't have a reset button, although later clone PCs quite often had a reset button on the front of the case. So just going to set this off, waiting for the power to be turned on. And when I turn the power on, what I'm going to do is wait after a second or two, then I'm going to press the reset button a number of times and we'll actually see what output we get. The power's on, reset once, twice, and a third time. So what we should see here is at the beginning, at the very early stages of the trace here, we'll see that in fact the power, even when the power supply has already been on, when I turn the button on, it takes a little while for it to stabilize. So you can see here there's probably a period of about 0.1 of a millisecond where it takes for it to stabilize. You can see also that the signal coming from the reset button takes a little while for it to come to a particular level. But then we can see that the reset signal here, within a few milliseconds, so if we put some timers on here, so from when the power really stabilizes, this time is what, about 5 milliseconds. So it takes about 5 milliseconds for the power supervisor circuit to actually put reset into a high state. And then we can see then that this is then held for about 400 milliseconds, so about 0.4 of a second. And then once the reset line goes low, then this means that the CPU will be able to start loading the BIOS and the operating system. You can then see here that we pressed the reset button low for a short period of time here. We did it for a longer period of time here, so you see we were in reset for a bit longer, and a shorter period of time here. And if we just have a look at some of these other signals, we can see that from the time when we release the reset to the end of reset here is about 411 milliseconds. This is designed to ensure that the computer only runs when the power is actually in a good and stable position, and in fact the power supervisor circuit that we have on the Breadboard PC, if the voltage were to become too low, then it will actually automatically reset the CPU until such time as the voltage returns to the correct voltage range. So that's the power supply power ready and the reset going low and the reset button handling. So what we're going to look at next is what actually happens to the Intel 8088 and 8086 CPUs when they come out of the reset state. And the best way how to look at that is actually have a look at the datasheet for this. So this is the Intel 8088 datasheet. So this has lots of information about how to make a simple computer. We did review this in some of the earlier videos at the beginning of the series. Now if we scroll down, it covers all the pinouts and all the various pin descriptions and labels, but the bit that we're actually interested in is it says down here, locations from address FFFF0 through 5Fs are reserved for operations including a jump to the initial system initialization routine. Following reset, the CPU will always begin execution at FFFF0, so that's 4 Fs and a 0, where there must be a jump instruction located. So really when the CPU comes out of reset, it looks at this memory address here to try and find some instructions to tell it what to do. And in general, most BIOSes will actually have a jump instruction there that will jump into the main body of the BIOS to start the initialization. So the CPU is going to, in fact, look, what it actually does is the code segment register is set to 4Fs and the instruction pointer is set to 0. So in fact, that works out to be that address FFFF0. So then we're going to try and find the BIOS. Now the BIOS is the firmware or the software which is built into the computer that handles the initial power-up process looking for an operating system. And if we look at the memory map on the Breadboard PC, we'll see that down at the bottom here we've got the reset vector or reset address that it looks for the first instructions, and we can also see that the BIOS and monitor, so the 32K EPROM, so electrically erasable read-only memory, that is at the address F8000 all the way up to the top of the memory there. And then the reason why we have to have this in the top of the memory is so that there is an instruction ready for reset. You can also see that in the Intel processor, in addition to this reset bootstrap jump here, the lower part of memory, so the first sort of 1K of memory, is actually dedicated to interrupt pointers. So we'll also see when we look at our memory map that the first sort of 1K of memory is actually dedicated to the hardware interrupt pointers. You can see here interrupt vectors, we've got 4 bytes times 256, so that takes up the first 1K of RAM. And we'll be looking at some of the other memory areas here as we look into more detail how the operating system actually boots. Now the Breadboard PC firmware and BIOS is in a single AT28C256, so this is a 32 kilobyte ROM. This is located at F8000 in the memory map and goes all the way up to the top of the memory. So the Intel 8088 and 8086 have a 1 megabyte address space. And the first 4K of this EPROM is in fact now the XT-IDE BIOS extensions. This is the code that knows how to interact with IDE hard disk drives. And then the rest of the BIOS and also the nanocomp monitor that handles the keypad and the LED display, that is in the rest of the 28K, including the reset code at the very top of memory. So now the CPU knows where to find the BIOS in EPROM. So you can see now we've handled the power on state coming out of reset and where does the CPU actually look to try and find the BIOS. So now let's have a quick look at the BIOS itself. So in the earlier videos we covered building the XI8088 BIOS. So this is some software that Sergey Kiselev has produced for his XI8088 XT compatible PC project. The listing, we do refer to the BIOS listing here quite a lot during the videos. I'm not going to go through this in detail, just perhaps if we go to the end of this. Now the only thing which is a little confusing about the addresses and things that you see in here is because our BIOS here is being set to start at F9000, then in fact some of the offsets here you have to kind of add a 9000 onto here. So in fact 9 plus 6 will end up being as F. So this is FFFE, and what this actually is doing here is saying pad out the BIOS code up to here to get to FFFF0, and we can see here that if we add the 9 onto here, this makes it an F. And what this instruction really here is saying is on reset, jump to the reset code in the Nanocomp monitor. Now if we wanted this to jump straight into the BIOS, then it would just be going straight to the cold start there, and that is the cold start for the main system BIOS. But because we have our little keypad here, what we do here is jump to the monitor for the keypad, and when we press the B key in here, then it jumps to the cold start here. So this is the BIOS, and there's a lot of things that the BIOS does. So if we just go and have a look at what the BIOS in fact does. So there's a startup sequence, and what the BIOS also does is output power on self-test code. So there is a power on self-test register on the Breadboard PC. So at the top of the board here, there's a fairly simple, just a single chip here with some address decoding on it, and that is a 8-bit latch. And what we do is we plug in the logic analyzer here onto here, and then we just look for when the value's been written to that, and that gives us a very simple power on self-test code which you can use to determine how far the PC's got to in booting things up. So when the BIOS starts up, it outputs some initial test tones, so it tests the timer and some of the parallel ports, peripheral interface adapter, sends power on self-test bytes to the post register, does initialization of the various chips in the PC, so the DMA controller, programmable interrupt controller, the programmable interval timers, the keyboard controller and mouse, working out what video controller is on the XT. Now the XT knew about the monochrome display adapter and the CGA, the color graphics array adapters in the BIOS, but any other video card, so VGA upwards, would actually have a video BIOS ROM actually on the card, and so it would then go and detect potential video BIOSes in the upper memory area and would run the video BIOS should one be found. So it initializes a video, looks for real-time clock and checks real-time clock, and if there's any CMOS backup memory, so this is battery backed up memory for configuration, then it'll actually read the configuration from there. So the very early PCs didn't have any CMOS backup memory, but most of the PCs in probably the last, 25, 30 years certainly will have had CMOS backed memory. Then it will detect serial ports, parallel ports. We don't have any on the Breadboard PC at the moment, and then looking for floppy disk drives, looking for how much RAM it's got. So the Breadboard PC has 512k at the moment, so half a megabyte. We'll then test the RAM that we'll see during the BIOS power on routines. You'll see it testing the RAM, and then it'll look for extension ROM. So similar to the video BIOS, other cards can actually have extension ROMs. So in fact, the XT-IDE hard disk controller that we're using has some extension ROM code, but we've actually merged that in with the main system BIOS. And then when it looks to boot the operating system, it first checks to see if we've pressed the F1 key to go into the CMOS setup, if we need to change the date or the time or any of the other CMOS configuration settings. Then it will look to load a boot sector from the floppy disk. I'm going to explain what a boot sector is in a few minutes. If it doesn't find anything on the floppy disk, then it will actually look to the hard disk if it can see a hard disk. And there's a thing called the master boot record at the very, very beginning of a hard disk. And this contains information for the BIOS to actually look to see what partitions are actually on the hard disk and what is the active partition. So then if there is an active partition, it'll then attempt to load a boot sector from the active partition. And we'll be looking at this side of the boot process later on in the video. So I've now modified the logic analyzer. We've now got the power on self-test ports. So what we're going to do now is we're going to power on the Breadboard PC and we're going to boot it up into the BIOS, and what we're going to do here is to record all of the power on self-test messages so we can actually see what's going on. So I'm just going to set this off. We'll now go and share the video capture. So I'm just going to power on the Breadboard PC, and as soon as the monitor comes up onto the screen, I will press the B key to boot the BIOS. we get the power on test noise. You can see here we've got the BIOS startup screen and it's testing the RAM at the moment. It's detected the hard disk, but it's now going to boot off the A drive because there's already a floppy disk in there with the MS-DOS 330 operating system in. So what we're going to do now is to have a look at the logic analyzer output, and we should be able to then see all the power on self-test messages that we see there. So this is our logic analyzer output, and you can see that we've got probably at least 30 seconds worth. And over the right hand side here, we've got the prefix of the 0 and the 1 here determined when we're actually writing the power on self-test port out here. And the reason for that is a little bit later on when we start to log the floppy disk drive accesses, sometimes it gets a bit confusing to work out when we're having multiple values the same, whether it's the head cylinders or sectors and things that we're looking for. Now what you can see here is that it starts off with the values of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and goes on to 12, 20, 21, 24, 25, 30, 31, 40, 41, 42, 43, and then logs a 0, and then we start to get these EE values. Now the EE values are where I've customized the BIOS to actually output the floppy disk seek parameters, so we'll have a look at those a little bit later. But what we can see here is these are power on self-test values, and if we go back to the BIOS, we can see in the error number power on self-test checkpoint codes that all the codes are actually listed out here. And so we can see down here all the various steps and things that it's going through. So in particular, all the early initialization with the zeros, locating video BIOS, initializing video BIOS if it finds it, all the things to do with detecting CPU and various other ports and things. The 40 is the BIOS extension ROM scan. So in fact, we had a 42 there, which meant that it had actually found the XTIDE BIOS extension, and there are also some other failure codes and things. So the power on self-test output port, if the PC was not booting properly, then this code here would give us some indication of what was going on. Now what I have also done is modified the BIOS code to actually output certain parameters. So you can see here as part of one of the BIOS int13, so this is the disk read and write routines, that in fact what this is doing is outputting the EE code. It's just a random byte that I chose to be unique to look for. What it then actually outputs then is the cylinder, sector, head and the sector count of what the BIOS is actually asking the floppy disk controller to actually read. So when we actually look at the power on self-test values, what we can see is that wherever we have an EE, then the next 4 values after that are the cylinder, starting sector, head and the sector count. So we can actually work out what's actually going on when we're actually reading the floppy disk in booting everything from this information. So in fact, when we look down here, you can then see that we've got all these EE values, and once we put in a filter here to only look at those beginning with a 0. So this is actually saying for cylinder 0, starting sector 1, head 1 and 1 sector, we're looking to do a read there. So what I will do is I'll take all that output and I'll put it into a slightly easier to consume form to actually work out what's happening. So what's actually happening when the BIOS is actually trying to look for an operating system? So what in fact happens is the BIOS does something called an int software interrupt int19 to actually boot the operating system. And in fact, in our XI8088 BIOS, what this does is a jump to the IPL initial program load function. And what this does is a loop that retries the floppy disk 4 times, given that floppy disks are quite unreliable, and so if there's any failure, it'll at least try another 3 times before it actually either tries the hard disk or throws up an error. So it does an interrupt 13 of operation 0, which resets the disk system, then actually gets some drive parameters. So the drive parameters are what determine how many sectors, tracks and things like that, in that obviously even with a 1.44 megabyte 3.5 inch drive, you could have a 720k floppy disk in there, for example. Then based on if there's actually a valid drive comes back from there. What it actually tries to do is to read one 512 byte sector using head 0, drive 0, track 0, sector 1. One thing that's a bit confusing of floppy disks is the physical sectors start at 1, whereas logical sectors and things start at 0. So this is one of the few areas where actually in the hardware we never have a 0 physical sector, it always starts at 1. And what the call to this floppy disk routine does is says load the first sector and put it at memory location 7C00. Now on the original PC this was by direct memory access, but what we did in some of the earlier videos, because we were having trouble getting the DMA controllers to work reliably, then I changed this to be programmed I/O, so the CPU handles the reading and writing of the data to the disk. So assuming that a floppy disk boot sector is actually found on the floppy disk and is loaded in the 7C00 all the way up to 7DFF, it will then check that there's a valid boot signature, so the magic numbers that appear at the end of the boot sector. So this is AA55, which is combinations of alternating ones and zeros. And then assuming all that passes, then the BIOS will actually jump to the starting address at 7C00, which is where the boot record then starts trying to load the operating system. Now the floppy disk operating system boot record is a bit different from the master boot record on a hard disk, and we'll have a look at that a little bit later. So what we're going to look at now is to have a look at the head 0, drive 0, track 0, sector 1 to actually see what does a operating system floppy disk boot sector look like. So here we are back on our A drive, having booted off the floppy disk. And if we just have a look at what I've got on this disk here, so some of the previous videos you'll have seen that we're using Norton utilities to have a look at a lot of these sorts of things. Okay, so we're going to explore the disk now, and what we want to do first of all is we're going to choose an absolute sector. So we're going to choose the A drive, and we're going to choose side 0 or head 0, cylinder 0, sector 1, and we're only going to read one sector. And then if we use the edit display item, so this is now showing us our operating system boot sector. Now what I'm going to do is I have actually taken this and disassembled it, and there's also a good reference site under Starman Ministry which I'll include the references for in the description below, which actually explains how all this works. But if we have a look at the top right hand side there, you can see that there's MS-DOS 3.3. So this is sort of the operating system sort of identifier. And if we switch this to look in text mode, you'll see that towards the bottom we've got some of the messages there. So non-system disk or disk error, replace and strike any key when ready, and disk boot failure. And there's also two file names down there, so io.sys and ms-dos.sys. These are the two main system files which are needed to actually start up MS-DOS. So what I'm going to do now is to show you some output where I've taken this boot sector and disassembled it using the NASM disassembler, and I've also used some of the helpful comments and annotations that the Starman Ministry site has done for an MS-DOS 5 boot sector. So here's a dump of the boot sector, and I've highlighted this using the same colours that the reference that I've got here. So this is the starmanpcministry.com, and there's a lot of good information on here about the boot records and all this sort of stuff. What he's actually got here is a very similar diagram, which is the MS-DOS 5.0 boot record with all these highlighting of the different colours. So what I've done is I've made use of some of the comments and things here, so I'm not going to publish these because he has specifically asked not to duplicate this information, but I will include them in the video. So the key things in this boot record are the first 3 bytes are in fact a jump, so EB34 is in fact a jump, and the 90 is in fact actually a no operation code. So this would be capable of potentially doing a long jump, but in fact when we look at the disassembly of the code, you'll see that it's basically jumping to this bit over here. Now this yellow here is the sort of operating system sort of identifier really here, and then the rest of this purple stuff here is known as the BIOS parameter block, or the BPB. Now this includes a lot of information about the disk format and number of sectors used for the root directory, how many sectors per track, etc. So all this sort of information about the format of the floppy disk. Then the boot sector code in green here, this is actually the code that this jump starts at, and what this does is actually tries to see whether or not there are actually these files. So you see the root directory file names down the bottom here, so ir.sys and ms.sys. So it tries to see whether these exist in the root folder of the floppy disk drive. If they do exist, then it loads these into memory, and it certainly loads io.sys into memory, and then it'll actually jump to the first line in the io.sys, which is the first part of booting up the MS-DOS operating system. So here's an MS-DOS 3.30 floppy disk boot record, and this is, the comments have been updated here based on the MS-DOS 5.0 analysis from the Starman PC Ministry, so thanks to them for that. So what we can see here is that we've got this jump short to 7C360 here, 36 here. So this is actually where the code starts. So what we do here, in fact, is we jump from here down to here. And this area here includes our MS-DOS 3.3 OEM system name. And there's lots of parameters here in the BIOS parameter block to do with what size our sectors are. So in all floppy disks and all, I think, all PCs use 512 byte sectors. I don't think there's any situations where the sectors are anything different. How many sectors are per cluster? Now we come to look at the hard disk, we'll see that there are 8 sectors per cluster, but on this we've just got 1 sector, 1 cluster, so it's a 1-to-1. How many reserve sectors we have for the boot record? How many file allocation tables we have? Based on the size of the root directory, how many entries can we have in the root directory? What the total number of sectors on the disk are. So because we've got 512 byte sectors and we've got 2 880 sectors, then that means we can have 1440 kilobytes. So strictly speaking, a 1.44 megabyte floppy is not actually 1.44 megabytes, it's actually 1440 kilobytes. Then there's a media descriptor. Now this particular media descriptor tells it that it's other, which means it's a 1.44 megabyte or 2.88 megabyte floppy disk drive. How many sectors are in the file allocation table? How many sectors are on the floppy disk track? So the 1.44 megabyte ones have 18 sectors per track. It has 2 sides. Now again, most floppy disk drives, modern floppy disk drives, have just 2 sides, but early floppy disks only had 1 side, certainly in the very early PC. And then there's some other stuff here that varies between operating system version, and certainly in later versions of DOS, then some of this information will be used for volume information, volume IDs and things like that. So the first thing the code here does is actually sets up a stack. So operating system stack, and it actually sets this to 7C00. So the stack actually works down from where this code is loaded. And that's a sort of a temporary measure until such time as the operating system actually establishes its own stack. Now, the confusing thing about this bit here is that some of this code is actually overwritten during initialization. So 7C2B to 3F. So this is from this section here down to, I think, 3F, which is a bit lower, is actually overwritten by the code. So in fact, this code here changes where the various parameter blocks, so this interrupt here is where the BIOS parameter block information on the default boot up of the BIOS is, and so there's a lot of fairly complicated things that goes on around here of moving things around in memory, but fundamentally what this is actually looking to do, once it's actually relocated some of the code around, is it resets the disk subsystem. There's various calculations to do with calculating the cylinders, heads and sectors into logical addresses and things. So this is where we're actually attempting to read the root directory for the floppy disk. And in fact, the root directory is actually loaded into 500 hexadecimal. If there's an error there, then we get the non-system disk or disk error. So it's looking for the io.sys and ms.sys in the root sector. If it doesn't find that, that's where you get this non-system disk or disk error. And this is the error routine here that does this. Basically, if we do find both of those, what it does is actually jumps over this code. So at CDA is where we actually continue to load. And so basically what this knows is that we can actually get the io.sys length actually from this particular byte in the root sector. So this is why it's essential that the io.sys and ms.sys are actually the first two files actually in the root folder. Otherwise, some of this code will fail. And the io.sys is actually loaded at the 700 hexadecimal. And what this code is then, the OS init loop is all about actually reading the io.sys into this memory area until such time as we get to the end of it. So once it's loaded io.sys into memory, it doesn't do anything with ms.sys, it only reads io.sys. Once it's actually loaded this into memory, what it then does is puts a couple of the parameters into the ch, dl and bx, in that some versions of DOS actually require some of these parameters to be passed into it. And then the actual starting of DOS is actually a jump to this address here. So this is jumping to 7000. This is in fact jumping to 0700. The segment is 0070 and the base address is 0, and so this actually results in this particular address. So at this point in time, then this boot code will have actually effectively started MS-DOS, and it's then up to MS-DOS or whatever operating system is running on here to actually start up. And if we look down the bottom here, there are a few of the routines here for displaying messages on the screen, for converting absolute sector numbers to sides and sectors, reading a sector into memory. This is some of the documentation for the BIOS, just to show what the register values are for passing parameters into the read routine. And then we've got our various messages, so non-system disk or disk error, replace and strike any key when ready, and disk boot failure. So these are sort of messages that come from the boot record. There are some other messages that actually come from the BIOS. So if the BIOS has trouble loading the disk, then there's a different set of messages. Then finally we can see the io.sys and ms.sys, and then there's the boot signature. So this is 55 and AA, or AA55. So this is the least significant byte, and this is the most significant byte. And this is combinations of 1010 or 0101s. So that's what the magic number is. So if the floppy disk actually has the valid entries in the root directory, then this should result in the io.sys being read into memory at 700. So this actually summarizes what we've got. So basically we jump over the BIOS parameter block, initialize the stack segment and the extra segment, so initialize some of the registers. We copy some of the disk parameters which are in ROM to RAM, and then we overwrite some of the ones which we've actually got in here. This is a very confusing area, particularly some of the MS-DOS initialization messes around with all this sort of stuff. So the disk parameters are a particularly confusing part of the operating system boot up. We change the parameters based on the floppy disk parameter block, and this is a location for interrupt 19, which is located at 78 hexadecimal. We do the interrupt 13 floppy disk read to look for the io.sys and ms.sys as the first two files in the root directory, and the root directory is actually loaded at 500. Then if that passes, we load io.sys into RAM at 0700, and then we start MS-DOS by jumping to this address. So the segment 0070 is the same as jumping to 0700, so 700 hexadecimal, if we'd said. And that's what's involved in starting the operating system. I'm not going to go into detail of how MS-DOS itself actually starts. Since the source code for MS-DOS 4 was released, then I did start to look at the MS-DOS 4 boot process, but it's really complicated and I'm not sure how much value you'll get from going into that. So what we're going to do now is to have a look at booting from hard disk. This is similar, but there is a step before we get to this boot record involving the partition table. So let's see what we've covered. So we've covered the initialization of BIOS. We looked in the post messages where we looked at it finding the extension ROM and running extension ROM, the fact that we've got the XTIDE BIOS. We've gone through the details of what the interrupt 19 to boot the operating system does, and we've looked at booting floppy disk. So now what we're going to do is to finally look at the booting the hard disk. So all we need to do now is to eject the floppy disk out of the drive. We'll power on the Breadboard PC again, and we'll look to see what the booting from hard disk does. So I'm just going to boot up the Breadboard PC. It's power on tune. So now once we finish testing the RAM, it's not going to try we'll try the floppy disk takes a couple of goes to test the floppy disk, and there's nothing there. Then it'll actually boot off the hard disk. So it's booted off the hard disk. It's a little faster. Now we've got the same utilities on here. Now there's a slight difference here in that if we actually go into Norton Utilities, we actually need to go into a different option to look at the partition record. What we're going to do is choose absolute sector. This allows us to check the C drive, and we can see here we're selecting side 0, cylinder 0, sector 1. So this is the first sector on the whole disk. And if we now have a look at this sector, you can see when we go into here in the Norton Utilities, it actually says, oh, it'll recognise it as being a partition table or a master boot record. So it actually shows us the partition table. If we actually go into the hex view, what you can see is where the flashing cursor is down the bottom here. This is where the start of the partition table is, and this allows for space for 4 partitions on a single disk, and only one of those partitions can be active. But you can see further up here we've actually got some of the code that executes actually when this is loaded into memory, and you can also see if we switch into the text mode, you can also see there's another couple of error loading operating system, missing operating system. So again, there's another set of messages we get from this code here. So again, Starman PC Ministry has a number of these master boot records with the disassembly of this. So what we're going to do is to have a look at that and see exactly what it does. But the key thing really here is it's looking for the partition table here, which actually tells us where our operating system is located. And we can see here that it's 3,267 sectors, so it's approximately 16 megabytes for our DOS partition that we have here. So this is a hex dump of that master boot record, so you can see there's the messages here, and we can see down the bottom here this is a partition table. And what I've done is I've run this through a disassembler, and I've used some of the Starman PC Ministry comments. So you can see it's a little different now, but it loads from 7C00, and basically what this does is sets up the stack segments and stack pointers and things in a similar way. Then with that, what this actually does is actually move some of this code to lower in memory to 600. This loop here actually copies all of the code in this master boot record down to 600 hexadecimal, and then it actually jumps to 61D here, which is this bit of code here. These comments here are from the PC Ministry site. So then what it actually tries to do is looks for the partition table. Is it bootable? So the byte, one of the bytes actually says it's 80 if it's bootable. If it's not bootable, they go on to the next one. If we've actually done all of it, then we'll actually get an error message. So we have none. It'll display a message now. Some cases it would be ROM basic, other times it would be another message if there's no active operating system found. So then this code here found an active partition. It reads the sectors, cylinders, heads. Now in this case it's actually going to be a little more complicated for a hard disk drive. It's not going to be just the 2 sides and up to 80 tracks like a floppy disk drive has. If there was an error here, then we'll get invalid partition table. When there's a problem, then it just goes into an infinite loop, just goes around in a loop forever. So if we've got a active partition, we're going to try up to 5 times. Now all the disk routines use the ES BX extra segment and BX register for the where we're actually loading this into memory. So we're going to be loading the boot sector now into 7C00. So the reason why this had to relocate itself is because this was initially loaded at 7C00 and then it's moved itself down to 600. And the reason for that is what it's going to then do is to try and load the operating system boot sector into the same area, so it would overwrite itself. So this is why some of this bootstrapping process can be a little bit tricky to get your head around. So then this does our interrupt 13 to read the operating system boot sector into 7C00. If it's the problem, then we will get a message error loading operating system and then hang. Then it will check to see if the boot signature is correct, so whether or not the last 2 bytes are the AA55. Remember, this is little endian, so the least significant byte comes first. So it's AA55 if you wrote it in its sort of hierarchy there. So again, if it's not, then it's not a valid boot record and it will lock up the system. But if it is a valid boot record, then it will actually do a jump to 7C00, and this actually starts again in the same way as when we booted off the floppy disk. This is the same process then from the floppy disk. And we can see down here we've got a couple of the messages: invalid partition table, error loading operating system, and missing operating system. Now the only difference is if we go back to our Norton utilities, what you can now do, we can now choose a different absolute sector, and what we're going to do now is rather than side 0 we're going to do side 1. And what this means is this is now the operating system boot sector, and you'll see here that we've got the similar information here, MS-DOS 3.3, and you can see the messages down the bottom. See the message down the bottom, and we've also got the io.sys and ms-dos.sys. So this is very, very similar to the floppy disk boot record. And what I've done is a similar process to compare this. So this is a comparison of the floppy disk boot record and the hard disk boot record. So I've got the same disassembled bytes here. You can see that the difference is here. On the left we've got the floppy disk, on the right we've got the hard disk. So the floppy disk has 1 sector per cluster, the hard disk has 8 sectors per cluster. This means that the smallest size that a file can be is 4K. We've got 2 file allocation tables on both, but then this is where the parameters are really different. So we can see that there are 512 possible root directory entries on the hard disk, but only 224 on the floppy disk. We have 2,880 sectors on the floppy disk, but we have more than 32,000, so that's 16 megabytes on the other one. We have a media descriptor, so F0 means it's other floppy disk, which means a 1.4 or 2.8 meg floppy, but F8 in fact is a media descriptor for a hard disk. We have the file allocation table, contains 12 sectors, where it's only 9 sectors on the floppy disk. There are 63 sectors per track, whereas on the floppy disk drive we only have 18 sectors. We have 2 sides on the floppy disk, but in fact, because this hard drive is using LBA mode or logical block addressing, then this actually uses the sides as 0 to 255. So this is how the LBA addressing works. And then there are some hidden sectors here, and the rest of the stuff is almost the same. So this shows that this sort of BIOS parameter block that is at the beginning of the boot record explains to the startup code and the operating system what the physical attributes of the disk is. And then at the end, the only other difference then was 1 byte at the end here. I'm not quite sure what that byte was for. So you can see that the floppy disk process and the hard disk process after this point in time, apart from the changes related to the physical media, then everything else is almost identical. Then if we just have a look at the root directory, so we can see here in the root directory that we've got the io.sys and the ms.sys, and it's important that these 2 files are the first 2 files in the root directory, because the BIOS boot code actually looks for the size information for the first file being io.sys actually from the boot code. You can see over on the right hand side these are read-only system hidden files, and in MS-DOS 3.3.0 you can't actually see these. There are some switches in later versions of DOS that you can actually see hidden files. One of the things you can also see down the bottom here is this disk was actually mounted in a later version of Windows, so in Windows 11, and you can see that Windows 11 has actually helpfully put some additional information. So there's some volume information there, and a system hidden folder. I think this is related to the deleted files and other system information. So this is the one downside: if you actually put any floppy disk or hard disk into a later version of Windows, it will actually put entries in here which can confuse the operating system. Certainly the operating system doesn't tend to show these. You can see that the utility here doesn't really know how to handle the Unicode data, I suspect, in here as well. So that's what happens to start up an operating system. I guess this video should have been called, what happens when you turn on your PC but we're afraid to ask. It's quite a complicated process that actually gets you to a basic operating system, and we haven't even covered the details that you need to know about on how the operating system itself starts. Needless to say, it's a lot more complicated even than this is. So hopefully this has actually been of interest. If you've ever wondered what happens when you turn on the power on a PC, particularly this is a PC running a classic BIOS rather than the modern UEFI BIOS. The modern PCs will have a different boot up process, but certainly any PC probably older than about 10 or 15 years old would have done this every single time you turn the power on, and it's actually quite amazing all the different moving parts that all need to align themselves in order for all this to work. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe and you won't miss out on any. And if you can hit like as well, it just helps to make the videos available to more people. In the background, I'm currently working on developing a CGA graphics video controller. It's going to take a few more weeks, so I'll do a few more of these MS-DOS related videos in the meantime, and then hopefully in sometime in early October we'll be able to do a whole series about making a CGA video card. Thanks for watching.